Hey everybody. Our next speaker, Daniel Dakhno, a funny story actually. We were talking about him on the podcast and I was like, finally put the name together with some other hacks he's done. He's done a bunch of AirTag stuff. This talk isn't about that, at least on the face of it. This talk is about hacking on a pinball machine. So please join me in welcoming to the Hackaday Europe stage, Daniel Dakhno.
Thanks, that's brilliant. Okay, thank you for the introduction, and also thanks for the previous talk, and for all the talks for that matter. I do have to make some admissions beforehand. So concerning the title, it used to read pinball machine instead of ding ding, but someone, who I'm not allowed to name, said that the title didn't have enough pizzazz. So I changed it, and that's all I'm allowed to say. Right, and also the title used to say hacking, or it does still say hacking a flipper machine. And I just realized that hacking means that you make something do something it's not supposed to. While we did, well, the exact opposite. We did make it do something it is supposed to. And that something is a pinball machine, right, as teased already. Sorry, I had to start my timer. So, just as a little forward, I have taken lots of ideas from another project of mine called Blanky, and I will explain on that later. And also on that note, the talk, what I find the most interesting about this whole thing is the general concept, which I have not seen before in that form. And well, I'm also obviously interested in knowing if you have seen something along those lines before. So now let's get to the juice of it. This is the pinball machine in question. It is a Gottlieb pinball machine. There's lots of history, lots of mechanics I know nothing about. And I tried. I tried looking into how it used to work, and no shot. For anyone who has never seen a pinball machine before, there's a metal ball that rolls around the field, the tilted field, and on the bottom you have, let's call them, I don't know what they're called, hitters or something. And by hitting a button, you basically activate the punchers, and they punch the ball back up. It was a group project, actually, and we received the machine with just the actuators and sensors. So talking about the sensors. Sensors are that simple. It's just switches. It's just two contacts, and when the ball hits one of the sensors, it closes the contact, and you can register that using a GPIO. The left one is a target. The 500-point thing, well, when you hit it, you get awarded points. And the right one is a bit more interesting because it is a sensor combined with an actor. So when you hit the mushroom thing, the sensor activates, and the mushroom triggers a mechanical reaction, and the ball gets accelerated. So this already implies some timing requirements, for that matter. And also, to finish the sensors, there's the coin counting, which essentially is also just two contacts closing. So really nothing too fancy. Now if we get to the actuators, it gets a bit more interesting. Because what you can see in, well, the lower middle of the pictures is solenoids. Most of you have probably heard of solenoids. It's an electromagnet combined with a moving part, and when you activate it, the moving part moves, and there's, well, some linear acceleration. And those ones are exclusively used as actors in a pinball machine. What you're seeing now is the beefiest ones. Those ones are responsible for the pedals, right, for the hitters. And the ball is actually fairly heavy. I don't know how heavy, but if you would hold the ball, you would say, wow, that is pretty heavy. So you do need some punch behind those actuators. Right, moving up, we have this music playing thing, which we, for some reason, spent an exorbitant amount of money on. So we can now play 3 notes, which is enough for the Mario tune. But this is also just solenoids hitting some metal parts. Right. Also, there's counters. Well, this is the back side of it. I don't have a picture from the front. But, well, from the front, you just see numbers. And those numbers are printed on a wheel, and the wheel is spun whenever your score changes. And as you might take a guess how the counters are actuated, exactly, it's all solenoids. So speaking of solenoids, I think the whole machine has 28 volts of voltage input. But if you push those 28 volts straight to the solenoids, you run into a bit of an issue because they get hot and they burn through. Great design, I know. Mechanically, this is solved by having a sensor inside of the solenoid. And whenever the solenoid is fully extended, the sensor triggers and turns off part of the solenoid. So there's enough power left in the coil in order to keep the thing on hold, but there's not enough power to make it burn. And this is the first challenge that we run into, speaking of the solenoids. They have fairly precise timing requirements. You need to actuate them. 2 milliseconds is an exemplary number. It's actually more like 20, but still. You need to give them around 90% of power to get them moving, and then 10 or 20% of power to make them stand still and not jump back, because there's a spring in there. And this timing needs to be fairly precise, because if you actuate it too short, it doesn't go all the way, so you don't get your reaction. If you actuate it for too long, for a bit too long, it might jump back and you don't get your result. So, right, this is how you have to control the solenoids. And to emphasize this, the scheme, the timing, and the power, they vary from solenoid to solenoid because for some reason, they were rewired at some point in time. So the parameters, they vary quite a lot. And also you have just differently sized solenoids in there. Right, so now we're suddenly talking about analog control. You need to output some analog signal to control them, right? Just a 1 or a 0 is not enough. And obviously, the first thing you think about is PWM. And you're right, I have no complaints about that. So this is the signal in a different dimension, essentially. You just output a 90% duty cycle for a certain amount of time, and then you turn it down. And this works. But again, the timings and the duty cycles, they vary from solenoid to solenoid, which there are probably a dozen of in the whole machine. So I think most of us, or everyone who has worked with Arduino, knows how we could implement this. Right? There's nothing really complicated about the code. Well, that is not 90%, that is a bit less, but whatever, it works, good enough. And our first thought was obviously to implement this, so for every solenoid to write a piece of code that is able to control it. But we have plenty of solenoids, we have multiple controlling instances, and that would lead us to, well, a lot of different code bases, which are mostly identical, but just vary in small parts. And we tried to come up with an alternative. And, well, we did. Now, why did I write 5 code bases? Because our whole architecture, our premise, our requirement was to use a CAN bus, right? And we decided on using a Raspberry Pi for the brain, for the controlling instance, for the whole logical operation. And also we decided to use multiple, we called them satellites, just STM32s, for the actual sensor readout and actuation of the solenoids. Now, suddenly we are in a bit of a decentralized structure. So you cannot put everything in one place. And since there's different amount of solenoids and different nature of solenoids on different satellites, that would lead us to a lot of different code bases, which are identical for like 80% of the code. So we tried avoiding that again. And after some time, we came up with these, well, let's call them restrictions, or rather with these principles that we tried to follow. So the satellites are supposed to be programmed, well, once is a bit of an understatement, but they're not supposed to be reprogrammed during the setup of the rest of the machine, right? So the idea is that we program the solenoids at the beginning of the project, and then we leave the code as it is. And also, we're not only supposed to program it once, but we're supposed to program it with an identical binary. Let's put it like that. So with a single code base that can be put on all the solenoids. The satellites. The satellites did have dip switches, so we could change their identity on the CAN bus. But apart from that, it was all the same code. And also, I started off with showing you a piece of Arduino code, which everyone could have written, obviously. But we wanted, or we were hoping to get away from that. We wanted this project to be maintainable by someone who is maybe not as proficient in writing C code, or someone who maybe doesn't know how to send out an analog signal. So we wanted to get away from code. We wanted to put everything into more configuration. So we wanted to have a configuration file that includes all the duty cycles, all the pin connections, right, the CAN IDs and whatnot. And the configuration was supposed to control, or well, actuators and sensors on, well, the other end. That configuration also was supposed to be held centrally, to be precise, on the Raspberry Pi. So the idea was not to distribute the configuration onto the satellites, well, not in its initial form, which I will show you later. It's a YAML or JSON, whatever. The idea is that the configuration is held centrally and that you can just log into the Raspberry Pi, change your configuration, and that automatically changes the behavior of your satellite, solenoids, whatever. So these were the principles that we came up with, and these are the principles that we, at the end of the day, stuck with. So I already touched on the configuration file, YAML, whatnot. Actually, we do obviously have to spread out information from the configuration file onto our satellites. But we did this in the form of a particular intermediate code, I'll call it. So there's some conversion happening before it gets distributed onto all the satellites. And the satellites, they then use this intermediary format to perform the job. This PWM signal you probably remember. Right, now let's touch a bit on the infrastructure, on how the data gets sent over, how this magic intermediary format. We were supposed to use the CAN bus, and no one had anything against it. Just to quickly touch on the CAN bus, a little refresher. The CAN bus is a differential pair bus, so it is suited to go over longer distances. It gets used in cars. That's its main purpose. Obviously, there's other places as well, but you'll mostly find it in cars because it's fairly robust due to the differential pair. It is multi-master, so each slave on the bus, it can turn into a master. So for a car, that would mean that, let's say you change the gears and your gearbox is connected to the CAN bus. The moment you change the gears, your gearbox sends out a signal. It doesn't have to be polled by some master. It just sends out a signal. But the other way around, all the devices on the CAN bus can also request the current gear from the gearbox acting as masters. And for our projects, that makes sense, because we do have quite a bit of sensors, after all, and having a bus where you can just spit out your sensor data is obviously pretty convenient. Using the CAN bus, you usually have a CAN controller, which implements a big part of the CAN stack. And you essentially tell the controller what data you want to get transmitted, and the controller retries until it, until it successfully spits out the data onto the bus. Why would this fail? Because you can have a collision, obviously. You can have two devices that decide to turn into a master at once, and both devices send out data, and the data collides. One of them sends a 1, the other one sends a 0, you get a collision. Now, CAN has a fairly clever mechanism where not only one of those controllers, the lower, one of those controllers, the one with the higher ID, it detects the collision and it just stops transmitting, while the other one, it continues the transmission and the packet is not impacted in any way. So even if you have a collision, it basically resolves itself without any impact to the quality of the data. Well, that adheres to the multi-master nature, essentially. And also, CAN has a little bit of a limitation. You can only send 8-byte packets, which may be enough to send out the current gear or the state of a sensor that changed, but it is not enough to send out our configuration logic. And thus, we turn to CAN Open. Just out of curiosity, who of you has heard of CAN Open before? OK, that's quite a lot. I'm sorry for every single one of you. CAN Open is quite the mess. It does have a lot of upsides, but it is, if you want to properly use and understand it, it is a lot. The benefits are, CAN Open introduces on top of CAN a thing called an object dictionary. An object dictionary is basically a collection of variables. Every variable has its own ID, and you can request variables from slaves, right? Or objects in this case. So CAN is just arbitrary 8 bytes, while CAN Open abstracts this away to, well, objects, variables. So you can send something that is comparable to a, let's say, GET request for a particular object. And this object can be the state of a sensor, it can be your gear, current gear. So CAN Open saved us from coming up with all of this protocol. Also, CAN Open provides profiles. So the data I just talked about, like the state of a sensor or a gear, there is standards defined in CAN Open, for instance, CIA 401, which is a standard for generic input-output modules, which our satellites are, right? And we implemented that. So using this profile, we could already set outputs, we could read in inputs, but still that was not quick enough, right? Relying on the CAN bus to control the precise timing needed for a solenoid, that's just not feasible. And so we implemented our own profile, which is a simple protocol for transmitting our configuration logic. Also, CAN Open has it has a protocol for notifications, for push notifications essentially, and it has heartbeats, which is nice. It's just included, it's turned on, and when a device dies, your CAN Open stack notices that, and, well, you can react on that. Still, it is a bit of a hassle because you need some C# Windows-based program. You configure your object dictionary, it spits out C code, you have to include the C code, whatever. Quite a bit of work, but, well, we decided on using that, and we did. Now, finally, let's resolve this whole item configuration intermediate logic thing. This is taken out of our configuration file. This is the configuration. This is the relevant keys for, well, one of the flippers, one of those big solenoids you saw at the beginning. What's important here? Well, first of all, it has an ID. So you can interface with this particular object item. Using the ID, yeah, you can interface with it. You don't have to know the CAN ID. You don't have to know the GPIO it's connected to. You can just use the ID that we can come up with, right, a string. We will ignore this microcode stuff for this slide, but this will get relevant. Here's the duty cycles. So this reads as when you want to turn on the solenoid, you have to apply 80% of power for 30 milliseconds, and then you just apply 20% for holding the solenoid activated. And then there's the analog channel over here, which is the pin that the solenoid or the MOSFET is connected to on the satellite. And the position we can also ignore for now, because the position is really not relevant for the whole operation of the flipper. Now to quickly touch on Blanky, the project I mentioned at the beginning. I found myself in a similar situation with my smart home a few years ago, and I created a project which has a similar preface. What you're seeing here, those are two boards, and they're, well, you see the scale over there, they're tiny, and they have a Nordic NRF52 on them. I bought like a dozen of those, and I built a firmware called Blanky, which I just flashed onto them. Let me peek, right. And if I, at some point in time, decide to use the board, I can just solder it into my circuit, I can attach it to my stepper motor, servo, to my water boiler, whatnot. And the moment it gets power, it turns on. I can connect to the thing using a website. I have to configure my pins, which takes from, let's say, 5 seconds to 60 seconds, depending on your amount of input-outputs you use. Well, and then you're done with the setup process, right? After you flashed Blanky, configured your pins, you can already interface with the digital outputs and the digital inputs. And while this is taken from my website, that is obviously public, you can use to play around with the I/Os. You can also replace the website with a Raspberry Pi or an ESP32 or whatnot in order to send the Bluetooth signals necessary to control the outputs and inputs. And this chip, with a CR2032 battery, it will last for about a year, right? Without any configuration or code needed. If anyone's interested, there will be a QR code later. Right, and for Blanky, I was facing the same problem that I'm facing with the flipper. I had to control a stepper motor, which controlled precise timing, which required precise timing, and also an end stop. So just controlling the stepper motor with a pulse of, let's say, 10 hertz, 15 hertz, it is not feasible with a low power, high latency Bluetooth Low Energy connection. So I needed a way of generating a precise waveform without relying on the transport, right? And here this comes in. This is also part of the whole Blanky project on the website. You can configure a sequence. This is a sequence of three steps, which is each applied for 100 milliseconds, and all of the 3 steps, the loop is repeated 10 times. And this, well, reducing this to 2, you could make an LED blink, or you could make a stepper motor move, or using analog signals, you could do something funny with a servo, whatever. And this sequence then gets uploaded using Bluetooth, using as few packets as possible to the chip running Blanky, and that one executes the code then asynchronously, right? And if your Bluetooth connection gets bad, it breaks up, or if there's latency, it does not impact the sequence getting executed. So this is why I came up with this, to control the stepper motor. And well, this rolled over into the whole Flipper project. Because now we have to look into behind the curtains of this whole, well, this whole mediocre-looking bootstrap GUI thing. Here I have to introduce another project which is called GPIO Assembler. It is a language which, in its complexity, is supposed to be comparable to an assembler. So you don't have any while loops, you don't have any ifs. You don't have to do any indentation. You have just basic commands which do a single thing. In this case, you have a command for writing output pins. Well, this turns all of them on. You can also skip them or mix ones and zeros. And you have a command for sleeping. Right. And this program, it just resembles a loop that blinks an LED infinitely with 1 hertz. And now, just for the completeness, there are 3, 4, or 5 more commands. There's a command to sleep, not for a particular time, but to just wait for particular input states. So this configuration, it waits until any or all of pin 2 and 3 matches a 0. You can also mix them. You can use multiple pins, one single pin, whatever. And there's also jumps. So you're seeing the label here. You're seeing the jump down here. This is an unconditional jump. So you can also perform jumps based on particular input conditions. This jump is only performed if the first pin is a 1 or the third pin becomes or is a 0. Not becomes, is. It has to be at that state at the moment of the evaluation. And we then took this tiny language and used it for our flipper. We used it for controlling the solenoids. And this is where this type microcode key value pair comes in and the solenoid code. Because we had a file lying around. It was a Jinja template, you'll see in a second. And it was called solenoid.jinja2, something along those lines. This is what this particular template looks like. For everyone who has already programmed in Python or done anything with Flask or Quart, this is a template. So essentially, it includes variables. And once you parse the templating engine takes all your variables, puts them in where appropriate, and spits out some parsed text. Or it complains if it can't find a variable and there's no default value. So some of you may have spotted it. For the ones who haven't, these are the keys that are present in the configuration. So the duty cycles, they get substituted into here, the analog channel into here. And once that is done, out comes this code. Most of the if conditions are irrelevant, they're not defined, they just get cut out. And as you might resemble, here we have 80% of power, 20% of power, 30 seconds in between, and an exit. We will ignore the exit, but essentially this generates us the waveform I was talking about. This generates us this jump, this step function from 80 to 20 after 30 milliseconds. So once we have this code compiled or once defined, or once the code changes, it gets compiled into a packet. This is comparable to Java. It's an intermediary execution format. It's not linked to the architecture. It's not linked to ARM or whatever. It's a very simple format. I believe that 00 is the command for. Forget about that. Somewhere in there is a command for setting the analog channel. Somewhere in there you'll find the 30 argument. So this packet, in case of Blanky, you send it over via Bluetooth Low Energy. In case of the flipper or the pinball machine, it gets transmitted using CAN, more precisely CAN open, to the satellite, which has multiple engines on board. Well, an engine is just a software implementation that is rudimentarily parsing this execution code. And there's multiple engines on the satellite because a satellite has different tasks. It either has different solenoids attached to it. Yeah, no, that's the only use case. It has multiple solenoids, and each of the solenoids needs to be controlled individually. That's why the first engine in this case is already taken. It's written to. We write this code to the second engine. We remember that this particular code is linked to, what was it? Flipper left outer, right? The idea over here. We remember that flipper left outer is linked to the second engine. And whenever we want to fire up the solenoid or the flipper left outer item, we just start the code execution. And our flipper, well, jumps up. Right, so there's that. So let's talk about the higher level control. We have now defined the configuration, so how we can define the parameters for different actuators and sensors. We have talked about how this configuration is turned into something usable by the satellite and something that actually translates to electrical signals. But now you might wonder how the overall higher level logic works. So we have a service running on the Raspberry Pi, which is called the item registry. The item registry parses the configuration file showed previously, and the item registry remembers what ID is what assigned to which engine, and the item registry is then able to speak can, or more precisely can open. Most of you have probably heard of dbus already. You have probably heard of dbus as something that is supposed to link together GUI applications. But we thought, why not misuse it for this case? After all, dbus is just meant for remote procedure calls. And that is what we need, because we wanted to have something similar to microservices. So this item registry service, it registers a standard free desktop, whatever, interface, and the interface has the following methods. It has a get method, which we didn't come up with. The get, set, and whatever, it's already defined by the dbus company conglomerate. I don't know. So the get method takes in an ID and spits out the current state for that ID or for that variable. Practical for us, because that's exactly how our items work. So calling the get method, you can just quickly fetch the item of a sensor or the counter value for the counter for a player. Analogous to the get method, as you might have thought already, there's a set method, which allows you to change the item, the state of an item, sorry. So if you were to call set with an ID of flipper left outer and a value of 1, well, you would have actuated the flipper. You would have started the process with the whole waveform, whatever, and the flipper would jump up, or the pedal. And also, just for completeness, there's a get all items function, which returns you a dictionary of each item defined in the configuration file and its state. But still, this doesn't really help us with the code. It makes it easier to interface with the items. It adds a lot of abstraction. It doesn't help us with any high-level logic. For the high-level logic, we wrote a Python library that allows you to write very simplified Python code in order to control the hardware. So in this case, to dissect this, we have a method, whatever its name is. It is supposed to be called when you press the left button. And thanks to our library, you can just use a decorator for that. And if you want to change the state of an item, which in this case are both left pedals, you can use the item proxy as you see here. So this part, this over here, is variable. You can write in there whatever you want, and as long as the thing you wrote here exists in the configuration, you will change its state, send a can signal, etc., etc. And as some of you have probably figured out already, this whole code, it just applies, it copies over the state of the button to the pedals, which you would expect from a flipper machine. When you press the button, the pedals should go up. When you release the button, the pedals should go down again. And this is what this function does. And since this was still too much for us, we simplified it even further. We had this helper method, which allows you to just make multiple items follow one particular item. So these two snippets, they have the same purpose, same logic. And well, using Python, then we described our game logic. So we described how the sensors and actors interact with each other. We described how many points are awarded for what target. We described how many balls you have. We described how the counters work, etc. And you might remember this little mushroom I showed you at the beginning, where there's a sensor in there, and the mushroom is supposed to actuate and accelerate the ball as soon as the sensor is touched. Now, you might think to yourself, okay, using a Raspberry Pi with a non-real-time operating system, CAN bus, the whole stack and so on, is maybe a bit slow for that. So the ball might have, by the time the mushroom actuates, if it is controlled centrally, the ball might be in a completely different place already. So for this mushroom thing, we had a piece of this microcode I showed you, which was doing the whole logic. So the microcode was waiting for the mushroom to trigger, for the sensor to trigger. It was then sending out the PWM in order to control the actuator, and well, it was repeating that until the sensor wasn't triggered anymore, which was the case in the first iteration already. So all of this infrastructure allowed us to not only control a whole flipper centrally using Python on a Raspberry Pi, which you can just log into and edit the code, but it also allowed us to give away tasks to the satellite, which are executed on the satellite locally with high precision without much more effort. Right. Now let's talk about a website. So we did need something shiny about the project. We needed something to show off, obviously. So we created this website. The website shows the picture from the beginning of the flipper machine, and you see the little red boxes. Each of the boxes is a sensor or an actuator. That makes it a bit more dramatic. Thanks. So using the website, you could see all the sensor values updating in near real time. And by clicking on one of the flippers down here, for instance, you could just make the flipper pop up, which was obviously extremely annoying for the person playing the flipper, but fun nonetheless. Or maybe that's the reason why it was fun. How did this work? Well, we did have a front end. We did have a website, which you're seeing there again. And we did have the item registry on the other side, which was presenting the dbus interface, and which was basically the gateway to all the hardware. And in the middle of it, we had the HTTP dbus gateway, which is another byproduct that spawned off this whole project. Initially, it was just meant for displaying the website, but it spiraled into something else. Maybe some of you have heard of dfeed or dspy already. The ones who have worked with dbus have probably heard about that. Let's say dfeed and dspy are programs like Postman or curl, just for interacting with the dbus. So those programs, they can show you your dbus, and then you can call functions, read in variables, receive signals, and so on. Unfortunately, those programs are written for GNOME only, and well, Linux in extension. But I thought to myself, what if I want to send out a dbus signal to start a systemd service from my smartwatch or from my fridge, which obviously all of you have been in that scenario already. Right, and that is what the dbus gateway turned into. So by now, the whole HTTP dbus gateway is its own project. It's a Python project, you can install it, run it. It will present a web server, and if you call that web server from a browser, you will see what I just described for dspy and dfeed. You will see your whole bus, you will see all the functions exposed, and you will be able to call them. You will also be able to read in signals, and so on. But you're not forced to use the front end. You can just open the developer console, check out how the protocol works, the HTTP protocol, and then you can use this as the REST API of the dbus gateway for controlling your dbus using HTTP without the front end. So just a quick note on this project that rolled out from all of this. Now let's quickly talk about our expectations and about the reality of how this turned out. Now this did sound a bit dramatic, I admit, because at the end of the time, we were all happy. It works astonishingly well. We did have a fairly robust system. When you press the button, the flipper, or the pedal reliably goes up. Everything works as it's supposed to, which is still hard to believe, half a year later. The whole system is fairly flexible. So you can take one of our satellites and put it into any other appliance, right? You could put it into a washing machine, you could put it into a car for 80% of the car's functions. You could put it into a smart fridge or whatever. And since it's basically just a gateway to the GPIOs, with the whole sequence and microcode thing, you could control heaps of other appliances and devices and actuators with our satellites without a pinball machine. You could use this for most smart home applications and so on and so forth. We did have a latency of around 30 milliseconds. Obviously, we were thinking about using some real-time Linux on the Raspberry Pi. It turns out we didn't need to. And if you play on the flipper and if you're not as experienced of a flipper player, you don't really notice the latency. There obviously is one compared to a simple relay, but it is very acceptable. And well, the reusability point I already touched on just a minute ago. And as you might imagine, it was heaps of engineering. Having to write a firmware for each of the 5 satellites, which just does its thing, would have probably been easier, but that's the path we chose to go. Let's talk about the outlook a little bit from what I learned about this. Sorry. So the whole idea, the constraints or the principles we set to ourselves turned out to be realistic, since the whole system works. We did indeed create this centralized, whatever, it's written there. We were able to have a central configuration that controls everything. We did have this stack of different layers, right? Which is good. The idea itself is as such validated, it works, but there probably will be no more work on this particular pinball project. The whole source code is obviously online. You can just read it. You can read the configuration file if you're so inclined. You can read every part of it. You can see the PCBs. But we will not be working on that particular STM32 implementation anymore. Rather, I would like to come back to Blanky, the project I mentioned at the beginning, or also in the middle. Since Blanky is currently tied to Nordic chips and also BLE as a transport, I want to get away from that. I want to take all the learnings from this pinball machine and feed them back into Blanky. I want to make Blanky platform agnostic, so you can run it on any platform, you can run it in a loop, you can run it on your PC. And I also want to get away from Bluetooth Low Energy. Obviously, Bluetooth Low Energy should still be supported, but there should be like a standardized packet format that can be used to convey the same information. So you can use anything packet-based, like CAN, SPI, UART, IP, TCP, you name it. Also, here's the sources, highly scientific. Well, two sources for the images, mostly. Okay, for everyone making photos, all of this is available right here. This is a link to my humble little portfolio. You will see all of my previous presentations, including this one, the slides, some of my projects, including this one, some notable fails of mine and what I learned from that, and maybe some interesting tools that other people made that you might find interesting. And with that, thank you for the attention. I hope it was somewhat interesting for you, and yeah, thanks for listening.
Thank you very much.